We're going to talk a little bit about mass spectroscopy. So, first thing, let's talk about a mass spectrometer. We've kind of got four boxes here, not four, three boxes here, okay? This first one, the vaporized sample is going to be put into. So we've got our little molecules, and they're going to be put in there. Now inside of this box here, once our sample is inside there, you know what, in fact, let's draw that. So once our sample gets put in here, we're going to ionize it. So what we're going to do is we're going to have, basically, let's zoom in here. This isn't too important, but I think it's cool. So we're going to have a little coil. I guess I should put it on the other side. Let's just do this. And then on the other side, we're going to have, let's do it this way, a positive charge. What that's going to do is it's going to shoot, this coil is going to release electrons. Pew, 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 okay? Electrons are just being basically shot at the molecules. And what's going to happen is these electrons will sometimes hit an electron in the molecule and knock that electron out of the molecule. So suddenly the molecule, which was neutral, somewhere in the molecule, an electron has been knocked out and now it is positively charged. If you knock out one electron, your molecule is going to have a +1 charge, okay? There's another thing that can happen and we'll talk about that. If you knock out more than one electron, so like 2 electrons, then it'll have a +2 charge, although this is much less likely because it's much harder for you to knock out an electron on a positively charged molecule than it is on a neutral molecule. Okay, so most of the molecules that are going to be bombarded with electrons are actually going to have only a single electron knocked out of them. Now, let's actually look at this molecule. So 2-bromopropane right here. Let's zoom in and let's look at the electrons real quick. You've got bonding electrons and you've got core electrons. So let's make the bonding electrons orange. Okay, so one there, one there, one there, one there. Here, 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 here. Okay, but then you also have core electrons. Let's make those yellow. Now, core electrons, you know, in most of organic chemistry, we don't care about the core electrons. We care about the valence electrons because the valence electrons are the electrons that are involved in making bonds and doing other cool stuff, right? But the core electrons still exist. We just don't talk about them. They don't do anything really that interesting. But they might do something interesting here. So I'm not going to draw all of the core electrons on the atoms, but I'll just draw, you know, a couple. So we've got some. Now, bromine is a massive atom, so it's actually got quite a few core electrons. I could look up the numbers, but I'm just not going to. Okay, so when we have electrons now, and they're going right, and they're passing by these molecules, right? What can happen is one electron can happen to boom, bump up and hit a bonding electron. Okay, and when that happens, you know, it's kind of like physics. They'll both change directions usually. What happens is this bonding electron goes bye-bye, okay? And then what happens to this molecule, well, I guess this electron, excuse me, is it's going to go on to the carbon, let's say, okay? We're going to look at possibilities. Oh no. All right, so now we won't have this bond here. We won't have that electron. And this electron is now a radical on this carbon. Okay, so let's make it a little bit bigger so we can emphasize that it's radical, but it's still the same electron that we were looking at before. Let's keep it the same color then. Okay, but now it's a radical. Now this carbon right here is now a carbocation, so it now has a positive charge because it only has 3 bonds. It's lost a bond, okay? So this part of the molecule is now an ion. It has a positive charge, and basically all of your positive particles and molecules are going to be attracted into this next section, okay? So this would be one of the molecules that goes into the next section, and we will use magnets to accelerate and then deflect these molecules. And so what it kind of looks like, wow, this is a bad drawing. So let's say this is a negative side, and this is the positive side of the magnet. Our positive molecules are going to change direction because when you have an ion that's subject to a magnetic field, it can change directions. The electromagnetic force will act on it. And it will hit the detector somewhere, and then that will be read by a computer and the information will be taken. But where it hits on the detector depends on 2 things. It depends on the charge of the molecule. Is it a +1, or did it happen to be one of those +2s, or maybe even a +3, right? Because the larger your positive charge of your particle, the more it's going to be affected by the magnetic field, okay? So charge is important for where it lands. The other thing that's important for where it lands is mass, okay? If you have a massive particle, it's going to be very hard to change the trajectory of that particle, okay? So it will be something like this versus a small molecule with the same charge would turn and change directions much more easily when both of those are subject to the same magnetic field, right? So where these particles hit on the detector depends both on the mass and the charge, and that's why in mass spectrum data, you are given the x-axis is a mass to charge ratio. So mass over charge. Now, usually this isn't much of a problem though, because like I said earlier, most of the time your particle is just going to have a +1 charge. Okay, it's much more likely for these to be +1 fragments, okay? So this little guy has a +1 charge, so it will go through and its trajectory will be affected by the magnetic field. However, this radical piece, it does not have a charge. If you were to calculate the formal charge of that carbon, it will be neutral. 1, 2, 3, 4, yeah. So with it being neutral, if it goes through and it ends up in the magnet, it won't be affected and it'll just go splat and it'll splat. But the other thing is, I'm pretty sure it wouldn't even get into this part of the system. But either way, this will not show up. However, there's a different way this exact same bond could have been broken, okay? So when I did this the first time, we said that the electron that was here in the bond got hit out, pew, right? And so this became the radical and this became the carbocation. But there is another possibility. What if an electron hits, oh wow, that did not work out, pew, hits that electron, right? And it goes boom, and it just roundhouse kicks it out of there, right? Then what happens to this electron? Well, it will go on to this carbon. And so what we're going to have is we will have a radical on this fragment, but we will have a positive charge on this fragment. Okay, and both of these possibilities occur, right, because we put in many, many molecules and we bombard them with many, many electrons. So we're going to have a lot of different possibilities occurring. So not only will we get fragments that are positively charged that are this size, like I showed you earlier, but we will also get fragments that are positively charged that are this size, little methyl groups. Okay? All right. Now, and that can happen with any bond, okay? But let's look at our positive charges real quick. Let's ignore the radicals. Yes, they form, but they don't end up really being of any focus, okay? Other than the fact that they were made because another positive fragment was made. All right, so let's just look at our carbocations, right? We're not going to look at the radicals. Which carbocation is more stable? The one on the left, let's call that A, or the one on the right, let's call that B. Well, B is a, oh wow, this is actually not a very good, okay, well, this is a primary carbocation, right? Because this carbon is attached to one other carbon. This is a methyl carbocation, okay? Plus, this carbon is attached to a bromine, which is to some degree electron withdrawing. So, molecule B has a more stable fragment if this bond that we broke breaks this way, where this becomes the carbocation. Because B is more stable, we are going to get more of these fragments than these fragments. So, when the bond breaks, we are most likely going to kick out this electron and have this be the radical, than the other way around, where we kick out this electron and this becomes the radical, okay? So it's a little bit of a probability. Both occur, but one occurs more often than the other. And how much carbocations or positive ion fragments you get, how much of a certain fragment you get depends on how relatively more stable it is to the other options, okay? Now, I also talked about core electrons. So core electrons, oh no. I'm just going to leave that down there. So core electrons can be knocked out by these bombarding electrons, just like the bonding electrons can be. So let's draw our little, let's connect these guys back together. And we had these orange electrons. Okay. So if we have electrons bombarding them and we happen to knock out, how about that electron right there? We happen to knock out a core electron. What happens? Well, such a good question. What happens is the molecule does not change any bonds, okay? But the molecule overall did lose one electron. So it will have a positive charge overall, okay? So we will have a positive charge on this, basically on the overall molecule, because this carbon lost an electron. But the cool thing is we didn't lose any bonds. And not only that, if we didn't lose any of the bonds and we didn't lose any of the atoms, remember, how much does an electron weigh in terms of mass, right? It pretty much weighs nothing. So you will have a molecule that has the same mass as before, but it's positively charged, which means you can have the entire molecule go through the mass spectrum machine, hit the detector, and it will give a mass over charge ratio. So mass over charge. In this case, the mass will be exactly the same as the full molecule we started off with, and the charge will be +1. So you know what? I should have prepared for this. I should have known what this mass is. Hey, Calvin?
Yeah.
Can you look up the mass for 2-bromopropane? I guess I could do that too. 2-bromopropane. So the mass over charge will be whatever the mass of your actual compound is over +1. Well, anything divided by 1 is just its number. Did you find it?
122.99 G/mol.
122.99. Let's round that to 123. Okay, so it'll be 123 atomic mass units over a +1. Well, that'll be 123. Perfect. That's what we have in our mass spectrum. I was just checking. Okay. Now, let's look at our chart here. Let's do a couple of things. Number 1 is the tallest peak that you have is called the base peak. Okay, the base peak is usually automatically set at 100. These are relative abundances, okay? So the tallest one is set at 100%, and all other fragments are relative to that. With the base peak being the tallest, the reason that the base peak is the tallest is because whatever produced this fragment here, this positive cation fragment, it just happens that that fragment is the most stable fragment possibility for all of our fragmentations, right? Because remember, when we split this up and we had 2 different ways of splitting it, there was a more stable version and a less stable version, right? The more stable version is more likely to occur, and therefore you will get more of those fragments, okay? So that's the base peak, the tallest. Right now it's at 43 mass over charge, but remember, most of the time the charge is +1, so that's basically the mass, okay? 43 will be the mass. Then you have the heaviest fragment, okay? So here, in this case, 124 is the heaviest fragment. Usually the heaviest fragment, it's reasonable to assume that it's the heaviest because it was a core electron that got knocked out of the system. And so that heaviest mass literally is the mass of your molecule, right? Because we knocked out a core electron, not one of the bonding electrons, so we still have all of our atoms, okay? So here, though, it's very interesting because we have 2 very similar peaks here, similar in mass and similar in abundance. See how they're about the same height, right? One's maybe just barely over the other, but they're pretty much equal. Okay, so that's very interesting. All right. Now, I want to talk to you a little bit about bromine and chlorine, okay, because this is very common. Depending on, now bromine has multiple isotopes, but the 2 most common are bromine 79 and bromine 81. And their abundances are 51%-ish and 49%-ish. So they're basically 50-50. Okay, so if a molecule has bromine 79, so the mass of this atom is 79, then the molecular ion peak, oh, I forgot to tell you, the highest mass peak is called the molecular ion peak because usually it represents the molecular molecular mass of the entire thing. In other words, the molecule has been ionized, but all components that make up the mass are still there, which is what I was talking about with the core electrons. So let's actually, what we're going to do here is we're going to add up the mass of this molecule, and for one of them we're going to pretend that the bromine is the isotope 79, and for the other one we'll add up the same, but we'll use bromine 81 as our bromine mass. Okay, so let's get a calculator out. Okay, so I have 3 carbons. So 3 carbons times 12, because the mass of carbon is 12. 3 times 12, 36. I should know this by now, but oh well. And then we've got 1, 2, 3, 4, 5, 6, 7 hydrogens. And the mass of hydrogen is 1, so that's 7. And then bromine. Now if we're going to do bromine 79, the mass of bromine will be 79. So that's just 79. So if I add this all up, 122. Okay, so if I had bromine 79 as my bromine mass, as the isotope for that, then my molecular ion peak would be 122. Right there. If I use isotope 881, what will I get? Well, this will be the same. So let me just copy that. Okay, and then 1 bromine, and this time it's going to be 81 equals, well, that'll be 124 if you add that up. And notice we have a peak for 124. Now the other thing you need to notice is, and I think I already mentioned this, is that because they're approximately the same height, that means that they occur with approximately the same abundance. Okay, we're getting the same number of fragments for the 122 mass fragment as well as the 124 mass ion. Technically, these aren't fragments actually, they're ions because we knocked out a core electron. We still have our whole molecule here. Okay. What do I want to say? I think that's pretty much it for that. Let's figure out how we get this 43 and I guess 27 and 41. There are other peaks here that do occur, but because they are lower abundance, I'm just going to kind of ignore them, right? But we could calculate how they come about. That just seems like a lot of work for me. Okay, so if we split this bond, which is actually what we were talking about earlier, if we do split this bond and we get this as a positive ion, which we said was more stable than this being the positive ion, of course both occur just at different abundances, at different probabilities, what would be the mass of this fragment, okay, if we got that? All right, so we have 2 carbons, so let me draw out this fragment. Bromine, carbon, hydrogen, CH3. All right, so we've got 2 carbons, so that'll be 24. We've got 4 hydrogens, so that'll be 4, and then we've got a bromine. And honestly, I don't know which bromine I should use for this. Let's go with 81, because I think these are together. All right. So bromine. All right, let's add all that up together. 28 plus 81, 109. Okay, so that didn't give us anywhere near 43. 109, but I don't know if you can tell, we do have a little baby fragment at 109. That's for the 81 isotope of bromine, and we also have a little baby fragment at 109. 107 for the 79 bromine. Okay, so we found those peaks, but they're pretty much small. So the probability of breaking the bond here is very, very low compared to our base peak. So, interesting. Even though I used that bond as an example, this data shows that this is not the bond that is significantly likely to be cleaved at, right? All right, so my next guess is that we're going to cleave off the bromine, okay? Actually, that looks like a pretty good guess to me. The reason I like that idea is because if, for example, the bromine becomes the radical and the carbocation, this propyl group becomes the carbocation, that forms a secondary carbocation, which is more stable than a primary, which is what we were just looking at. And of course, it's more stable than a methyl. The other thing is that if bromine becomes the radical, right, bromine is going to be more stable in terms of holding that extra electron because it's such a large and polarizable atom. So I like this idea where I think it's very likely that the bromine gets to become the radical and the propyl forms a secondary carbocation. The question is, what's the mass of that? Well, let's see. So we've got 3 carbons. So that'll be, I'm just going to start doing this. That'll be 36 plus 1, 2, 3, 4, 5, 6, 7 hydrogens. And yeah, that's it. So 36 plus 7 is 43. And that explains our highest peak, our base peak. In other words, that is the most probable ion fragmentation that we will get, which is pretty cool. I think that's awesome. So now we know, if the question was, what's the most probable fragment that will occur? That is a positive charge. It would be this carbocation propane. If they ask, what's the most probable fragment that ends up being not charged or that is a radical, it would be this bromine radical. And this bromine radical wouldn't be measured because it's not charged. So it wouldn't go through the detector and be measured. Wouldn't go through the magnetic field and be measured. Now I could do more. We could go and figure out how this 41 is created and how this 27 is created. Oh, great, like an easy way to know if you have a bromine atom in your molecule is to look at the largest peaks. And if they are separated by a difference in atomic mass that equals the bromine's difference in atomic mass for the 2 isotopes, so 79 and 81 have a mass difference of 2 atomic mass units. So, and that's exactly what these peaks show. But the other really important thing to look at, and it'll just make it so obvious, is that the peaks' intensities are almost equal. And the reason for that is because bromine isotopes 79 and 81 naturally are abundant at almost the same amount. Okay, 51, 49, it's pretty much 50-50. If we had a molecule with a chlorine ion in this, right, there are 2 main isotopes for chlorine, chlorine 35 and chlorine 37, okay? Now, the interesting thing is the abundances for chlorine 35 is about 75%, and for 37, it's about 25%. So if you were given a mass spectra and you looked at the molecular ion peaks, which are the heaviest peaks, and it had a chlorine instead of a bromine, instead of seeing this, right? Well, I guess I'll draw it over here. We would see right, what's the difference between 35 and 37? It's still 2 atomic mass units. So let's say this is atomic mass unit. And this is atomic mass unit plus 2, right? Because it depends on how big your molecule is, where your molecular ion peaks will be. But your intensities will be relatively they'll be about the same ratio as this. So 1, and this will be about 3. So you'll have the lower atomic mass unit peak will be 3 times more abundant than the atomic mass unit plus 2 peak, right? Because this is the 37 isotope and this is the 35 isotope. Because the 35 isotope is about 3 times more abundant naturally, just in the world, than chlorine 37's isotope. And so that's kind of a giveaway if you have halogens.